In this lesson, we'll complete learning target number 3 and discuss molar volume and Avogadro's hypothesis. We'll also begin learning target number 4 and discuss the ideal gas law. So far in this unit, we haven't discussed a gas law that involves moles, the amount of a gas in the sample. Avogadro's hypothesis deals with this. We'll touch on it briefly, but really it's a stepping stone for a more important law. Avogadro's hypothesis says that the volume of a gas varies directly with the number of moles at constant temperature and pressure. We can represent this with N varies with V. If you add more gas, your volume is going to increase. No brainer there. We can derive this into a math equation by introducing a constant. For Avogadro's hypothesis, it's K5. If I do initial conditions and rearrange for K5, I'm going to get N1 over V1 equal to K5. And then if I change the amount of moles, then I can get some final conditions, and that'll be N2 over V2. So Avogadro's hypothesis, written mathematically, is N1 over V1 equals N2 over V2. Now the conditions on this is that P and T need to be constant, and because the volume's changing, we need a flexible container. Now there are a couple of assignment questions where you can use Avogadro's hypothesis, but once Avogadro derived this relationship, he started measuring the volumes of gases and compared them to how many moles were in them, and defined a new physical property that can be measured. Molar volume is the volume of 1 mole of a gas. The equation is mv equals v over n. Don't get this confused with the molar concentration of a solution, which is defined as C equals n over v. What Avogadro noticed when he was comparing different gas samples was that at STP, all ideal gases have the same molar volume, and he determined this to be 22.4 liters per mole. Now you can use this as a shortcut. Instead of using other laws that we'll discuss later, if you have any gas at STP and you know the volume of the sample, if you divide it by 22.4, then you'll know how many moles of gas you have. Because the volume is dependent on the temperature and pressure, molar volume changes under different conditions. Example 1 gets us to calculate the molar volume of a gas sample. At 90 kPa and 20 degrees Celsius, a 4.6 gram sample of hydrogen gas is found to have a volume of 53 liters. Here we're asked to calculate the molar volume. I can sub in what the volume is. It's given in the question, 53 liters, but I don't know how many moles the sample contains. I am given enough information to find it though. It says in the question I have 4.6 grams. I can use the mass equals moles times molar mass equation from Unit 3 in order to calculate the moles in the sample. Hydrogen gas is a formula H2, so its molar mass is going to be 2.02 grams per mole. I can now sub in what moles equals and complete the calculation. Now I can only keep 2 sig digs because of my 53 liters. So I'm going to have to round this to 23 liters per mole. Now example 2 shows you the Avogadro shortcut. Here I have STP conditions and the volume of a gas sample is 63.7 liters. It asks me how many moles are in the container. Because I'm at STP, I know the molar volume is equal to 22.4 liters per mole. That's the constant for any ideal gas. If I have 63.7 liters, I can rearrange and solve for the moles of the sample. I can only have 3 sigdigs in my answer, so I'm going to round to 2.84 moles. Now there's a couple of options to solve example B. Here it tells us we take our original sample, 2.84 moles, and we add 3.76 moles to it. This gives us 6.60 moles of gas in our total sample. Now I could sub this into Avogadro's hypothesis. My initial moles would be 2.84, my initial volume would be 63.7. My final moles would be 6.60, and I'd solve for V2. But because I know I'm at STP, I like to use Avogadro's molar volume shortcut. I know the molar volume is going to be 22.4 liters per mole. If I want to know the volume of my sample, all I'm going to do is take 22.4 and times it by 6.60 moles. That gives me 147.84 liters, but I can only keep 3 sigdigs in my answer, so I'll round that to 148. Today we'll also talk about the ideal gas law. It was developed so that we had all the influences of gases in one equation. How it's derived is by combining Avogadro's hypothesis, the volume of a gas is directly proportional to the number of moles of gas, with the combined gas law, which involves the relationships between temperature, pressure, and volume. To derive this, let's start with the relationship of Avogadro's hypothesis. We know through a proportionality statement that volume is directly related to the moles of the gas. So if you increase the number of moles, the volume of your gas sample increases. We also know from Charles's law that volume is directly proportional to temperature. So if the temperature goes up, the volume goes up. And we know from Boyle's law that volume is inversely related to pressure. So if pressure goes up, volume goes down. To get rid of the proportionality sign, the little fish, and make it an equal sign, we need to introduce a constant. Most people would think it's a k, but because this is a special law, the constant we introduce is actually r, and this is the first constant we're actually going to learn what the value is and use it in the equation. We're not going to do our math magic and get rid of it. So v is going to equal rnt over p. Scientists usually rearrange this equation so that it's a single line of text with no fraction. And when you do that, you often see the form, which we'll use, is PV equals nRT. Now there's only one condition on this equation. Temperature has to be in Kelvin. You also need to know what the value of R is. So let's figure that out by taking a fictitious 1 mole sample of gas at STP. If we sub in the values, at STP the pressure is 101.3 kPa. Because I have a 1 mole sample at STP, I know the volume is going to be 22.4 liters using Avogadro's molar volume shortcut. By definition, I have a 1 mole sample. Let's get lots of sig-digs on this, so we'll put 1.000. We're going to solve for R, and at STP, the temperature is 273. If you rearrange for R, I'm going to figure out what these are equal to times each other, and then divide them by 1 and divide it by 273. R equals 8.314. Now the thing is that R only equals this value if you sub in volume for liters, kPa for pressure, and Kelvin for temperature. If you use torr for pressure or mils for volume, then R is going to equal some other number. So it's always important to convert into kPa, liters, and Kelvin before using PV equals nRT so that you know what the value of R is. Let's try out example number 3. What volume would 2.32 moles of H2 gas have if held at 105.3 kPa and 25 degrees Celsius? We know a lot of gas laws, but the ideal gas law is the only one with moles, temperature, pressure, and volume in it. So I'm going to start by writing down that equation. I'm going to sub into it what I know. My pressure is 105.3 kPa. I'm looking for the volume. I've got 2.32 moles. R equals 8.314. And my temperature converted into Kelvin is going to be 298. If I rearrange and solve for volume, I'm going to get 54.6 liters. Let's try out example 4. How many moles of CO2 are there in a sample of gas with a volume of 18.2 liters at SATP? This is an important question. It highlights the fact that we can take physical properties of a gas that we can measure, like volume, its temperature, and the pressure we have the container at, and actually figure out how many particles or moles are in that container. So I start with the ideal gas law and sub in what I know. At SATP, the pressure is 100 kPa, the volume is 18.2 liters. I want to determine the amount of moles. R equals 8.314, and at SATP, I'm at 25 degrees Celsius or 298 Kelvin. When I'm rearranging for N, I'm just going to take 100 times 18.2 and divide by both of these terms. That turns out to be 0.735 moles. Because now we have gas laws with moles in them, we can add a new branch onto our mole map. It's a little difficult to rearrange the ideal gas law, and we didn't want to have 3 boxes here, one for P, V, and T. So what we did is said, if you know the pressure, the volume, or the temperature of the gas, you can rearrange the ideal gas law to find the number of moles. Or if you have the moles and 2 of these physical things measured, you can rearrange ideal gas law and find the third. Complete the Avogadro's hypothesis and ideal gas law questions listed on your Unit 5 assignment cover sheet.